Your machine learning system predicts customer churn with 89% accuracy. Your large language model generates helpful explanations and recommendations. Leadership wants them combined. Predict who will leave, then explain why and suggest interventions conversationally. The integration seems straightforward until the language model starts hallucinating reasons for churn that contradict what the machine learning model actually learned, a grounding failure we examined in depth in part 22. Customers get explanations that sound authoritative but are statistically wrong. This is what happens when you connect machine learning to language models without understanding the integration architecture. This is connecting machine learning to language models without breaking either. ML Part 26. How to integrate machine learning and language models without creating unreliable systems. Part 1. What actually needs connecting? Machine learning systems output predictions, numerical scores, classifications, probability distributions. A churn model outputs customer ID 1234, 73% churn probability in the next 30 days. A fraud model outputs transaction XYZ, fraud score 0.92. A demand forecast outputs products SKU 456, predicted sales 2,347 units next week. These are structured outputs designed for downstream systems to consume programmatically. APIs read the scores and trigger automated workflows. Dashboards display the numbers, business logic routes based on thresholds. Language models operate on text. They generate natural language explanations, answer questions in conversation, and produce human-readable content. They excel at making information accessible but struggle with numerical precision and factual consistency. Connecting them means bridging structured predictions to conversational interfaces. The machine learning does the quantitative work. The LLM makes results understandable and actionable through language. Part 2. Integration patterns that work. The read-only presentation layer. LLM accesses machine learning predictions as context, but does not modify or reinterpret them. A customer service agent retrieves churn scores from the machine learning system and includes them in the LLM context. Customer 12345 has 73% churn probability. Generate retention talking points. The LLM creates conversational suggestions while treating the score as factual input, not something to explain or justify. This pattern works because it separates concerns. Machine learning handles prediction accuracy. LLMs handle presentation and interaction. Neither tries to do the other's job. The structured query interface. The LLM translates natural language questions into structured queries that machine learning systems can answer. User asks, which customers in the Northeast are likely to churn this month? The LLM converts this to parameters the machine learning API understands. The machine learning system returns structured results. The LLM formats them conversationally. This pattern handles the translation layer. The LLM is a query builder, not a predictor. The machine learning system remains the source of truth for predictions. The orchestration layer. A separate component manages workflow between machine learning and LLM systems. The orchestrator calls the machine learning model for predictions, validates outputs, enriches the business context, then passes structured data to the LLM with explicit instructions on what can and cannot be modified. The orchestrator enforces guardrails, preventing the LLM from contradicting the machine learning outputs or hallucinating explanations. This pattern works for complex workflows where multiple machine learning models and LLM interactions need coordination with business rules enforced at each step. Particularly irrelevant to parts 18 and 19, it is worth noting for future discussions that LLMs are not exclusively a top-of-the-stack component. In modern knowledge graphs and retrieval architectures, LLMs increasingly participate in how data structures are built and relationships are predicted, not just how results are presented. This is a deeper architectural conversation than this series has ventured into, but it is where the most interesting and production questions are currently being asked. Part 3. Integration patterns that break. LLM interprets machine learning outputs. The machine learning prediction gets passed to the LLM with instructions to explain why this customer will churn. The LLM has no access to the features the machine learning model used or patterns it learned. It generates plausible sounding explanations based on general knowledge about churn, not this model's specific reasoning. The explanations sound authoritative but may contradict what the model actually learned. Machine learning predictions in LLM training. Organizations fine-tune LLMs on machine learning model outputs, hoping the same LLM will learn to predict directly. This confuses what each system does well. LLMs are not designed for numerical prediction accuracy. They generate text that resembles training data. An LLM trained on churn predictions might generate plausible-looking probability scores that have no statistical validity. Bidirectional modification. The LLM can modify machine learning predictions based on conversational context, or the machine learning system tries to learn from the LLM outputs. This creates circular dependencies where neither system has a clear authority. Errors compound rather than cancel out. Part 4, or integration complexity hides. Latency mismatches. Machine learning interfaces might take 50 milliseconds, while LLM response generation takes 2 seconds. If the integration requires sequential calls, total latency becomes 2+ seconds. For interactive applications, this feels sluggish. Parallel processing, where possible, and caching machine learning predictions for common queries helps, but require architectural planning. Failure mode differences. Machine learning models fail by returning low confidence predictions or errors when input data is malformed. LLMs fail by hallucinating plausible sounding responses that are factually wrong. When connected systems fail, you need monitoring that detects both types of failure and handles them differently. A machine learning error should block LLM response generation. An LLM hallucination should not override a valid machine learning prediction. Context window limits. LLMs have finite context windows. If you need to include extensive machine learning predictions, feature explanations, and business rules in the context, you hit limits quickly. Summarization strategies that preserve necessary information while fitting context constraints require careful design. Version synchronization. When you retrain the machine learning model, does the LLM need updating? If the LLM is generating explanations based on old feature sets or outdated business logic, it produces misleading guidance even if the machine learning predictions are current. Keeping both systems synchronized as models evolve requires operational discipline. Why this matters. The value proposition of combining machine learning and LLMs is real. Machine learning provides numerical predictions grounded in data patterns. LLMs make those predictions accessible through natural conversation. Together they can deliver experiences where users get accurate predictions with understandable explanations and actionable recommendations. But the integration architecture determines whether you get the best of both or the worst of both. Poor integration creates systems where the language model undermines machine learning accuracy with hallucinating explanations that have no grounding in the knowledge layer, or where the machine learning precision gets lost in vague conversational responses. Understanding connection patterns early prevents building duct tape systems that work in demos but break under production use. The question to answer up front: what is each system's responsibility? Where's the handoff point? What happens when either system fails? How do you maintain consistency as both evolve? In closing, connecting machine learning to language models requires architectural patterns that bridge structured predictions to conversational interfaces. Integration patterns that separate concerns work. Patterns that blur responsibilities break. Understanding where complexity hides in latency, failure modes, context limits, and version synchronization explains why some AI systems feel coherent while others feel like disconnected components forced together. The architecture determines whether you combine strengths or compound weaknesses. In Part 27, Edge Machine Learning versus Cloud Machine Learning, where inference actually happens, and why the semantic layer we covered in Parts 14 through 24 changes the deployment decision in ways most edge versus cloud comparisons ignore.